I wanted to show you the mistake I made here on 37. Okay, so the sequence square root of 2n over n plus 1. Look, I can see that the 1's going to be ignorable down there when n gets really, really large, and I'll just have 2 times something gigantic over 1 times something gigantic, and so I'll be getting the square root of basically 2 times n over n. It'll be the square root of 2 as n goes to infinity. But I made this mistake. See, I wanted to look at the difference between the sequence evaluated at n and the thing I think it converges to. To do that, I got a common denominator. All right, and square root of 2 times the square root of n plus 1. Well, I just combine the square roots there and multiply the 2 through. All right, so that put me here. Square root of 2n plus 2 is decidedly bigger than square root of 2n. So I just wrote that. But then I started going to inequalities. I said, in order to make that expression bigger, let me just chop off the minus 2n there. I think that was a big mistake. Because take a look at what happens. Then I'm left with square root of 2n plus 2 over the square root of n plus 1. Now, here, shouldn't I have an expression that goes to 0 as n goes to infinity? I mean, the idea is to have the difference between the sequence and square root of 2 go to 0. So I want this thing to go to 0 as n goes to infinity. But looking at it, similar argument, I think I'm going to get square root of 2 there, right? And carrying through with some more inequalities, I replaced 2 with 2 times n, something even bigger upstairs, and n plus 1 with something smaller, n plus 0 downstairs, and that gave me this. Now look, I've simplified to 2, and so I think I made a big mistake right here. I mean, this was a true statement. It's just that it gave me something, an expression that does not go to 0. So I'm looking at this and thinking what I did is I replaced the numerator with something bigger than the numerator, but I added too much. Right? I added square root of 2n. And that makes sense to me, because square root of 2n plus 2 minus square root of 2n, those two things are about the same size, right? So you've got an infinity minus infinity right here. And what I did is I got rid of one of those things that was going to infinity, and ended up with just a thing that was going into infinity. Instead of infinity minus infinity in the numerator, I just have infinity. So I took away too much. So let me just remove that from my solution right there. Okay. And what I'm going to do is, a student once told me, when in doubt, multiply by the conjugate. And I see this kind of situation where I have the square root of something minus the square root of something else in the numerator. So I'm going to multiply the numerator and denominator by square root of 2n plus 2 plus the square root of 2n. See, I've done it on the denominator, and now I need to do it in the numerator. When I multiply by the same thing in the numerator, what I will get is, let's see, the cross terms vanish. That's the cool thing about multiplying a minus b and a plus b, and that's why you multiply by the conjugate in general. Right, the cross terms vanish, and all that you're left with is 2n plus 2, the square root of that squared, and minus 2n, the square root of that squared. Ah, yes, this simplifies quite nicely. See, now I've got that infinity minus infinity kind of structure, but the infinities cancel each other quite nicely. So I'm left with the 2 upstairs and downstairs all this gunk. Ugh. Let's see, instead of an equal sign, let me put in a less than or equal to sign. Okay. Now, in order to make this guy bigger, I want to make the denominator smaller, so I will simply not add this square root of 2n. Or maybe I just won't add this 2n plus 2. No, I won't add, but just for clarity's sake, I won't add the square root of 2n. So here we go, 2n plus 2. All right, so now the denominator is smaller, so I've got a bigger expression. I'd like to further simplify, so let me write this as 2 over square root of n plus 0. See, now I'm replacing the denominator with something smaller to obtain a bigger fraction. And square root of 2n plus 0. Okay, so I've just gotten rid of those pesky constants sitting out there. Now I could say that this is, let's see, square root of n times square root of n, that's going to give me just an n down there. And I got a 2 over square root of 2, so that'll be a square root of 2 upstairs. Lovely. And that's less than epsilon when n is sufficiently big. N is bigger than what I will define as n epsilon. This function is going to depend on epsilon. And it will be, looking over here, I want it to be square root of 2 over epsilon when epsilon is small, 1 over epsilon is huge. And that's probably not going to be an integer. I want an epsilon to be an integer, so I'll apply the ceiling function, and there we go.